Welcome to The Explainer. Today, we're taking a little trip, about 93 million miles away actually, to look at an absolutely alien landscape. We're talking magnetic tornadoes, superheated bubbles of plasma the size of Alaska, and massive eruptions that literally shoot matter into space at 2 million miles per hour. We are going to explore the terrifying, awe-inspiring, and just crazy complicated engine of our closest star. Let's dive into the complex machinery of the Sun.
So to kick things off, we really have to ask the most pressing question of all. What happens when the Sun gets angry? We usually think of the Sun as this warm, constant, life-giving force, right? But it absolutely has a dark side. It is fully capable of unleashing violent solar storms that could act like a giant cosmic tsunami, basically crashing the electrical grids that power our entire modern world. Just imagine your world suddenly going totally dark. No satellites, no cell service, no long-distance communication, no power to keep the fridge running or even the water pumping. You're practically going back in time overnight.
And look, this is absolutely not just science fiction. Back in 1859, the world experienced what scientists now call the granddaddy of geomagnetic storms, the Carrington event. During this superstorm, the auroras were so intensely bright that miners in Colorado actually woke up, made their coffee, and went to work because they literally thought it was dawn. But it wasn't just pretty lights in the sky. The massive electrical surge hit the only real critical infrastructure of the day, the telegraph system. Lines overheated, offices caught on fire, and as one historical report noted, an operator was burnt so badly he actually had to be hospitalized.
So, a modern solar storm? It's a terrifying 1-2 punch. At exactly 0 minutes, a solar flare erupts, releasing a blinding burst of X-rays that hit Earth almost instantly. But the real monster comes 18 to 48 hours later. That's the coronal mass ejection, or CME. It's basically a massive wave of billions of tons of electrically charged particles. If that hits us with full force today, the surge could completely melt our critical 125 kilovolt transformers. And here's the kicker. These transformers take months to build. In a worst-case scenario outlined by the National Academy, it could take up to 10 years for a full recovery. We'd literally be chopping wood in the backyard just to survive.
Because of that threat, there's a massive urgency to figure out how this star actually works. But until the 1960s, scientists were stuck doing what they joked was solar dermatology, just looking at skin-deep surface features. Then they had a massive breakthrough. It's called helioseismology. They discovered that the sun's surface actually vibrates, just like ripples on a pond, and those ripples are caused by sound waves passing right through the sun's interior. The best way to think about it is like a giant pipe organ playing 10 million different frequencies all at once. Churning gases deep inside send these sound waves rippling outward. If you play a low, deep note on a pipe organ, the sound comes from a long, deep pipe, right? While on the sun, those deep frequencies bring back information from way down deep in its core. High notes give us information about the layers closer to the surface. By deciphering those 10 million frequencies, scientists can actually map the hidden inner layers of the sun.
Which brings us to the anatomical map of our star. We are going to take a journey right down into the belly of the beast. We'll start at step 1, the core, where nuclear fusion happens. Then we'll track the birth of a single photon of energy, follow it out through the radiative zone on a random walk, move up into the churning plasma of the convection zone, and finally hit the surface, where sunlight and flares are explosively released. Let's start at the very center. 15 million. That is the temperature in degrees Fahrenheit at the core of the sun. This region is only about a quarter of the sun's total size, but it's 25 times the diameter of the Earth. It's the absolute powerhouse of our star. Everything we experience on Earth, every ray of sunlight, every bit of heat, and the terrifying effects of those solar storms, it all starts right here in this unimaginable heat.
But what exactly is the core made of? It's way too hot to be a solid. It's too hot to be a liquid. And it's not even a normal gas. It's a completely different state of matter, a gaseous soup of charged particles known as plasma. Deep inside the core, the immense weight of the sun crushes hydrogen gas until the atoms literally break apart into electrons and protons, creating this extremely dense plasma.
Now, plasma might sound totally alien or sci-fi, but you're actually familiar with it. You see plasma in fluorescent light bulbs, fancy TVs, and neon signs. The closest natural example we have here on Earth is lightning. But keep in mind, while a lightning bolt reaches tens of thousands of degrees, the sun's core is 15 million degrees. It is radically, unfathomably hotter.
And under all that extreme temperature and pressure, something incredible happens.
Nuclear fusion. Protons smash together to release tiny packets of heat and light called photons. The scale of this is just staggering. Through this atomic alchemy, the sun converts over 4 million tons of mass into pure energy every single second. To put that into perspective, that's the equivalent of 10 billion hydrogen bombs detonating in the core every single second.
Which naturally begs the question, with 10 billion hydrogen bombs going off every second, why doesn't the sun just blow itself apart? Well, it's all about a perfect balancing act. You have all of this explosive fusion pressure violently pushing outward, right? But the sun is so unbelievably massive that the sheer pressure of its own gravity is constantly pushing downward. Gravity pushes in, fusion pushes out, and that perfect equilibrium is the only thing keeping the sun intact.
Okay, so our little photon of light has just been born in this chaotic nuclear furnace. Now it has to escape. It enters the thickest layer of the sun, the radiative zone. But the plasma here is incredibly dense. The photon can't just fly straight out. Instead, it does what physicists call a random walk. Imagine trying to walk straight across a really dense, crowded party. You bump into someone, say hello, bounce off, bump into someone else, and change direction. That's what happens. The photon furiously ricochets in a zigzag pattern, being continuously absorbed and spit out by plasma particles.
And that right there creates one of the most mind-bending timelines in the universe. Even though that photon is moving at the literal speed of light, that random walk through the dense radiative zone takes it over 100,000 years. Once it finally hits the thinner convection zone, it still takes about a month to rise to the top. But then, once it finally breaks the surface, it sprints 93 million miles to Earth in just 8 minutes. Which means the sunlight hitting your face right now was actually created during the last ice age. How crazy is that?
So what exactly happens in that month-long phase before it reaches the surface? It enters the convection zone. Think of this zone as a 125,000-mile thick lava lamp. Heat enters from the bottom, causing blobs of plasma to heat up, rise to the surface, cool off, get dense, and fall back down. If you look at the surface of the sun, you can actually see this bubbling structure, which is called granulation. These bubbling cells of plasma are literally the size of the state of Texas, and they frantically rise and sink in a mesmerizing cycle that lasts only about 12 minutes.
And guys, this is where the complex machinery of the sun really shifts into high gear. We have this bubbling, churning plasma, but the sun doesn't spin like a solid ball. It acts like a fluid. The equator rotates faster than the poles do, and the layers beneath the surface also spin at completely different speeds. When you combine this bubbling motion with this uneven spinning, you create a massive magnetic dynamo. It stirs up incredibly powerful electrical currents, turning the sun into the biggest electrical generator in the entire solar system.
So this dynamo generates intense, invisible magnetic field lines that run all through the sun. But because of all that churning and uneven spinning, those lines get stretched, twisted, and braided together. Imagine taking a coiled spring and winding it up tighter and tighter and tighter. Eventually, the immense strain causes the magnetic field lines to kink upwards, poke right through the surface, and cross each other. When a positive and negative line cross, they short circuit in a colossal explosion of energy, and that is what we call a solar flare. Now, here is something absolutely wild that has literally defied physics for decades. It's about what happens just above the surface, in the sun's atmosphere, known as the corona. The sun's surface is around 10,000 degrees Fahrenheit, but as you move away from the surface into the corona, the temperature skyrockets to 32 million degrees. Think about how weird that is. Normally, if you walk away from a campfire, it gets colder, right? On the sun, you walk away from the surface and it gets 300 times hotter. Scientists have only recently discovered that high-velocity jets of plasma shoot up like licks of flame, delivering this unbelievable heat directly into the atmosphere.
And this extreme heat, that is the trigger for our cosmic tsunami. The immense heat of the corona acts like a raging gale force wind, constantly pushing on the plasma that's draped over those twisted magnetic field lines. It billows them out like sails on a ship. And when those lines finally snap and short circuit, the sail is cut loose. 1 billion tons of highly charged plasma is flung out into space at 2 million miles per hour. That is the coronal mass ejection, the CME wave heading straight for Earth.
Now you might be wondering, how often do we have to worry about this? Well, the frequency of these terrifying storms all depends on the sun's 11-year cycle. The sun actually has shifting personalities. After the magnetic poles reverse, the sun enters what's called a solar minimum. The magnetic fields are subdued, things are calm, and there are very few dark sunspots on the surface.
But over the next 11 years, that dynamo winds the magnetic fields up tighter and tighter until the sun reaches solar maximum. It gets angry. The fields become incredibly tangled, sunspots multiply, and those massive CMEs explode outward much more frequently. Which brings us to our final and honestly pretty critical thought. Thanks to incredible satellites like NASA's Solar Dynamics Observatory, we can see the sun's complex machinery in unprecedented, super high-resolution detail. We understand the dynamo, the plasma, the 11-year cycle better than ever. But predicting exactly when and how powerfully a solar storm will hit Earth, that's still mostly a guessing game. We've dodged the bullet time and time again, but as we continue to build our lives entirely around fragile electrical grids, we really have to ask ourselves, when the next big one inevitably strikes, will we be prepared for the perfect storm? Thank you so much for joining me on this incredible journey to the center of our star. Keep looking up, stay curious, and I'll catch you on the next explainer.